Hello, everyone. This is the last in a series of lectures about Chapter 35. Today we'll be talking about total internal reflection. So, when light enters the interface of two mediums, it will split. Some of it will transmit to the new medium and some will reflect back. Then that means that the energy is split somewhat between the ray that transfers out and the ray that reflects in. For a light beam traveling from a medium where it moves slow to one where it moves faster, such as, water to air, light will always be refracted away from the normal. And eventually, that means that if you increase the incident angle at which you strike the normal, the angle of refraction will be bigger and bigger by Snell's law. Eventually, what happens is that the reflected ray will become brighter and the refracted ray will become dimmer. Most of the energy starts going into the reflection of the light beam rather than its refraction. Once the incident ray reaches an angle such that the angle of refraction becomes 90 degrees, so it's perpendicular to the normal, it's right on the boundary of the two mediums, the refracted beam will vanish and the entirety of the beam will be reflected, reaching what's called total internal reflection. So if we use Snell's law, then we can derive a general rule for total internal reflection that for any medium with index n1, it has some critical angle, theta c, such that the angle of refraction is 90 degrees. It's perpendicular to the normal. And any angle, any incident angle that's bigger than the critical angle will not cause any refraction at all. So anything past the critical angle, light will not refract, it will only reflect. And again, this only happens when you're moving from a high index medium to a lower one, since if it was the other way around, light will bend towards normal, and you will end up in a situation where light can bend so much as to be perpendicular to the normal. This leads to some really cool effects, such as the photograph of the swimmer here. Since the photo was taken underwater, you can see that all the light emitted by the swimmer and the ground on the water on the pool is totally internally reflected at the surface of the water, so it can reflect back and into the camera, which is why the top of the water in the picture looks like a mirror. Any sort of deformations that appear in the reflection is just the turbulence in the water. Diamonds also take advantage of internal reflection since they have a high index of refraction and they have a very small critical angle of about 26 degrees. So that means that any incident light in the diamond that hits any of its sides from inside at an angle more than 26 degrees will just be, all of it will just bounce off inside the diamond. It will all get totally reflected. So a really well crafted diamond, one that's really well cut, it'll work like the one shown in this ring here, where it'll be cut in such a way that light can enter the diamond through the top few facets, and then the light will kind of bounce off the bottom part of the diamond. It will reflect completely, and then it will refract back in direction parallel to the ray that hit it. So kind of like a retro reflector, where most of the light, is kind of coming in It's kind of doing a U-turn and coming back at you, which is why diamonds are so shiny, because they're able to take advantage of total internal reflection to stop most of their light from passing through it, but rather catch most of the light and reflect it back so that it looks shiny to anyone admiring a diamond ring. Also, since the angle of incidence, has to be bigger than the critical angle, that means then that as long as you're within the critical angle, light will still pass on to the new medium. So there's this phenomenon known as Snell's window, where if you're taking pictures from, say, underwater, um, there's like a 90-degree or so cone around the field of view of your camera that will be able to see through into the air above, because within that cone, light is within the critical angle, so it can still pass through the boundary. But outside the cone, it just reflects in all of it internally, so you can't see past the water outside of the cone, which gets the name Snell's window. So a quick quiz here. You have 5 light rays entering a glass prism, and the question is, okay, how many of these undergo total internal reflection? And you'll note that they're almost parallel, and what's happening is that the prism, although it's mostly perpendicular to the rays on the left end, on the right end it's slanted. And what the slant does is that it makes the incidence angle bigger as you go from top to bottom. So that means that for the first one, the angle of incidence isn't too big. It's probably somewhere around 45 degrees. But then if you look at the second one from the top and the third one, you see that it's a lot farther from the normal. Let's say the third one's probably close to like 70 degrees, I'd say. And if you look at the bottom two, there's no light on the other side of the prism. There's no refraction there. It's getting totally reflected. But it's also worth pointing out that in the bottom surface of the prism, the rays, all of the 5 rays do pass through, because all of them are incident within below the critical angle, right? They're pretty much hitting the bottom surface of the prism at pretty much perpendicular to the normal, so they're gonna transmit through. It's also worth pointing out that since the bottom 2 rays are being totally reflected in, they appear the brightest in their internal reflection. While the bottom 3 rays, since they are able to pass through the prism, they do also reflect in the prism. You can see like faint rays on the bottom left of the graph. Most of the energy goes to the refracted rays rather than the reflected ones. So it's 2 rays that get totally internally reflected on the slanted surface of the prism. Now, the second part asks about rotating the prism, and the question is, how would you rotate it so that all 5 rays experience total internal reflection? So what you have to do is rotate the medium so that the angle of incidence increases, because you got to up the angle of incidence to create total internal reflection. And to do that, since you can't move the light beams, you can only move the medium. You want to move it so that now the normal between the medium and the light beams, there's a bigger gap, right? There's a bigger angle. And that ends up being the counterclockwise direction. So if you flip this triangle counterclockwise, you can kind of picture it that you're kind of moving if you look at the refracted rays on the right side, and you can imagine the triangle moving counterclockwise, you can kind of see how the beams would be closer to the side of the prism, and if they're closer to the side of the prism, then they're farther away from the normal. So meaning that their incidence angle would increase. And eventually, all of them will be past the critical angle, causing them all of them to reflect internally and go down to the bottom. One more thing to talk about is optical fibers, which basically take advantage of total internal reflection to move light from one end of a cable to another. And usually they're come in bundles of this like light flexible rods. And again, you can just picture this as some material that keeps sending light through one end to another in the same way that wires carry currents. These are kind of small fiber cables that carry light. And this allows for pretty fast transfer of information since light does move fairly fast in them. I believe the material has an index of refraction of about 1.4 or so. The way they're usually constructed is that there's two layers to it. There's a glass or a plastic core surrounded by a cladding, and sometimes there's a jacket to prevent any kind of external damage. And the way it happens is that light just kind of keeps moving along the wire, keeps bouncing off the core of the optical fiber, and since most of it's just getting reflected, then it doesn't lose too much of its energy. It doesn't lose a lot of its intensity as it travels long distances. In fact, any loss in intensity is basically just due to reflections occurring on two ends, or the fiber material absorbing the light. So something sometimes done by physicians to do a colonoscopy, right, lets you view parts of the body that you can't normally see without cutting someone open. Or even just if you need to cut someone open, you can stick an optical cable there as a sort of like fiber optic camera to kind of poke around the insides of somebody without having to make too much of a large incision. And yeah, so they're really good for long distance communications. There's a lot less information loss compared to something like wiring or coaxial cables for telecommunications. So they're more reliable in that way. I mean, every system has its downsides, but optical fibers have proven to be a very good development. And also, there's some cool uses for them, such as little like light fixtures. So, kind of part A, the textbook kind of says that it's showing an example of how optical fibers are combined to make a single optical cable, and that's usually what you see in telecommunication companies to transfer information. But I think it just looks really cool. And if you go shopping at IKEA, you can get some lights that take advantage of fiber optics to look cool, kind of like an alternative to neon signs, but with less neon, just lights. And that's why, while many computers, you still have your USB ports or such to carry information. A lot of equipment now also has optical ports for that as well. And what else was I gonna say? I believe that there was somebody won the Nobel Prize. Charles Kao, Dr. Charles Kao, yeah, won the 2009 Nobel Prize in Physics by basically discovering the way that optical fibers could be used to carry information over long distances. And it's not a simple process, by the way. There's a long distance telecommunications is quite an interesting field where the signals have to be converted and interpreted by many devices, from electrical pulses to light pulses and back to electrical pulses. It's quite an interesting field. Anyways, that's it for chapter 35. I hope you can join me next time where we'll be talking about some mirrors and lenses. So you can look forward to that. And I wish you all a good